Good morning, friends. I'm Gopal Agrawal and student of biotechnology from NIPER Mohali, and I'm here again with my second video. And this time we will going to discuss introduction to association, dissociation constant, and Hill equation. And let me first some brief you that this is an important topic for those who are preparing for the life science in GATE and also for the GATE biotechnology. So let us today again turn starts with some of the basic terms, right? And the first term that you're going to see is about ligand, right? So a ligand is a molecule that has been bound reversibly by a protein, right? So protein can be your enzyme, right? Enzymes are all protein in nature, they have protein in nature, right? So ligand may be any kind of molecule including another protein. This means that a protein that has been bound to another protein, right? So that's the meaning of a ligand may be any kind of molecule including another protein. For example, antigen and an antibody. Antigen is also protein in nature, antibody is also protein in nature, right? So antibody can be act as a ligand to the antigen, right? So after binding to the antigen there may be a change in the conformation of the antigen, right? So that's the basic meaning, right, of the line that ligand may be any kind of molecule including another protein. So it can be antigen, antibody. Another thing is binding site, right? A ligand binds at a site on the protein called the binding site, right? So on the on the surface of the protein there may be a specific site for a ligand to bind, and that is called as a binding site. And then there is a induced fit, means the binding of a protein and its ligand is often coupled to a conformational change in the protein that makes the binding site more complementary to the ligand, permitting tighter binding. So it means that when the protein and the ligand they have been bound, right, there is a conformational change in the proteins get conformationally changed, right, and that makes the binding site more complementary to the ligand. It means it allows the change in the shape, it allows more tightly the ligand to bind to the protein, right? And the structural adaptation that occurs between the protein and ligand is called induced fit, and these kind of change in the conformation, right, it is called as the induced fit. Active site is a ligand binding site is called as the active site or the catalytic site. So now we will see in a very short what the four terms means, right? So this is a protein, right? This is a ligand that has been bound to the protein, right? Now this is called as a binding site. So this will be the binding site of the, because this is a place, actually this ligand will occupy the whole space, the space will not be there, it's just been seen, but actually there is no space here. So the whole this is ligand, right? And this is a binding, this is the active site, I should say this is the active site over here, right? Is the active site, because here this is a protein and this is a ligand and the binding is done over here. So now once this ligand is bound to the protein, there is a change in the conformation, right? And this is called as a induced fit. Now quantitation of a protein ligand interaction. See, function of any protein does not depends on the association of the protein to its ligand, but also its dissociation. It means once a ligand has been bound to the protein, it is important for the associating of the ligand to the protein, but it's also important that this ligand get dissociate from the protein, right, in order that the protein gets back to its normal conformation and it's does its function, because every protein needs to does a function that is been needed, right? Overstimulation of any protein, overstimulation of any antigen, right, it may leads to has a hazardous effect, believe me. So thereby we will now see how to quantitate. See, we are now quantitating the protein ligand association and dissociation. So in general, the reversible binding of a protein P to a ligand L can be described by a simple equilibrium expression, and that is P plus L is equals to PL. So P is a concentration of the protein, L will be the concentration of your ligand, and this is equilibrium to the PL, that is the how much is the protein and ligand they have been bound. So protein that has been bounded to the ligand, that is the concentration of the protein that has been bounded to the ligand, that is the PL. So this reaction is characterized by equilibrium constant Ka such that Ka is equals to concentration of protein that is been bound to the ligand upon total concentration of protein to the total concentration of the ligand, right? And the term Ka is the association constant, right? So now we are seeing, now in order to find out how much is the ligand bound to the protein, right? So first you should know how much is the protein bound to the ligand, what is the concentration of the protein that has been bound to the ligand, right? What is the concentration of protein that you are having, what concentration of ligand you are adding to it, right? So on the basis of this, right, you can determine the association constant and you can know the affinity. How you can know the affinity is, association constant provides a measure of affinity of the ligand L for the protein. So higher value of Ka, if this value is high, it denotes a higher affinity. It's, you can see from the equation, Ka is equals to PL divided by P by L, right? It means that Ka is directly proportional to concentration of protein that is being bound to the ligand. If there is a higher concentration of this, it means that more protein is been bound to the ligand. And when there can be a more protein bound to the ligand, when it has a higher affinity, when the ligand has a higher affinity for the protein. So thereby this value is high, it usually indicates that a Ka value is also high, and therefore it indicates the higher affinity of the ligand for the protein. So now let us see a very useful term, that is a binding equilibrium, right? And that is a theta, usually denoted by the theta, and that theta is nothing but the binding sites occupied by the total number of binding sites available. And this can be similar to the, if we just compare this, we can just compare this with the equation of PL upon concentration of protein, concentration of ligand, right? Because binding site occupies, it itself suggests the protein that has been bound to the ligand, right? But for the time's sake, you can remember this theta is equals to binding site that has been occupied divided by total number of binding site that have been available. So if there are 25 ligand binding site and ligand binds to the 10 sites only, then the value of theta will be, theta is equals to binding site occupied upon total number of binding sites, and that is equals to 10 other binding sites that have been occupied, and total number of binding site available was 25, so the value is 10 by 25, that is 0.4. Now the value of Ka can be determined from the plot of theta versus the concentration of the free ligand L. So here we are having the plot of theta versus L, right? So the concentration of the ligand at which half of the available ligand binding sites are occupied, that is theta is equal to 0.5. Why 0.5? 50, if we consider as such way that 50 are the binding sites that have been occupied from 100, right? So the value of theta will be 0.5, that corresponds to 1 by Ka, right? And so you can say this is a theta value, right, that is equals to 0.5, and this is the Kd value, right? So this is abbreviately I can say this is a 0.5, this is a half the concentration of the ligand at which this binding sites have been available, and if you extrapolate it on the concentration of ligand, right, So you are going to get over here is Kd, right? You are going to get over here is Kd, and Kd is nothing but a dissociation constant, and Kd is inverse of 1 by Ka. So we are getting both the value of Kd and Ka from this graph. So Kd is the equilibrium constant for the release of the ligand, and Kd is equals to inverse of Ka, that is P concentration of protein into concentration of ligand divided by concentration of protein bound to the ligand. So when L is equals to Kd, that is dissociation constant, half of the ligand binding sites are occupied. So you may be thinking how this is. So you can see this theta is equals to L, right, upon L plus Kd. So this is the equation, right? It is the concentration of theta is equals to concentration of ligand upon concentration of ligand plus Kd, right? So that is equals to concentration of ligand divided by concentration of ligand plus concentration of ligand, because Kd is equals to L, that is equals to L by 2, right? It is equals to L by 2. So as the concentration of ligand falls below Kd, progressively less of the protein is bound to it. So when you have the value of the L, concentration of the ligand decreases below the dissociation constant, right? So that is less protein that has been bound to the ligand. Because why? Because more ligand has been then dissociating it. So lower value of the Kd, it denotes the higher affinity, and the higher value of the Kd is denotes less affinity for the ligand to the protein, right? So also you can see this, in order for the 90% of available ligand binding sites to be occupied, concentration of the ligand must be 9 times greater than the Kd. So this can be simply explained by Kd is equals to 90% have been occupied, right? So it is by divided by 90, and 10 will be then available, right? So the 10, so that you will going to get, that is the 9 will be the answer. So now let us have some exercise like, right? So they are the protein, this is a ligand that have been bound to it. So you can see there's the biotin, insulin, various ions like nickel, calcium. These are the various proteins, right? And this is the Kd value, dissociation constant value from it. So now I will ask you a simple question, that which protein binds more tightly to the ligand. So here the answer will be based on, you have to see the dissociation constant value. Have you seen it? Okay, so the list is of avidin. So avidin is having the least, and thus it binds ligand biotin more tightly. Right, for a protein with the n binding sites, right, the equilibrium equation will be then P plus NL is equilibrium to the concentration of P and L. So well, n will be the number of the available binding sites, right? And the expression of the association constant will then becomes PL upon concentration of P by concentration of L, right? And this raised to n. Then the theta will become concentration of ln raised to n upon ln plus Kd, right? So this has been taken from the Larringer, right? So you can refer Larringer in order to see this in much more detail, right? Here basically it's the same that was been earlier, right? But there is a difference only in the n. Here just we are taking it as a with the n number of binding site, right? So if you know the how many binding sites have been available for the protein, right, for the ligand to bind to it, right, you can find the association value from the equation. This Ka is equals to P ln upon PL raised to n. You can also find the theta value, right, from this equation. And then if you want to find out the concentration of any of the term, that is concentration of L, concentration of Kd, right, knowing the other two terms, right, you can also find out from this equation. So this equation 5.16 is a Hill equation, right? And if you plot this value of this, right, it is a y is equals to mx plus c. So you will intercept will be minus Kd, and the slope will give you the number of the binding sites that are being available, right? So this, in this way, you can utilize the Hill equation, right, to find out, right, the number of the concentration of the ligand. You can find out, you can also find out dissociation constant, you can find out the what fraction of the uh, binding site has been occupied of the total available, right, and you can find out the concentration of ligand also. Now let us see some questions that have been given from the Larringer Principle of Biochemistry, written by D.L. Nelson, M.X. Cox, 4th edition, chapter 5, protein function, page 189. So protein A has a binding site for ligand X with a dissociation constant of 10 raised to minus 6 molar. Protein B has a binding site for ligand X with dissociation constant of 10 raised to minus 9 molar. Which protein has a higher affinity for the ligand X? So again you have to see, so and okay, I will explain your reasoning and convert the dissociation to the association constant for the both proteins. This is a very simple exercise that has been in the Larringer. So first, protein B has a higher affinity, right, because it has a lower dissociation constant value, right. Secondly, Kd is equals to 1 by Ka, so thereby Ka will be 1 by Kd is equals to 1 by 10 raised to minus 6, that is equal to 10 raised to 6, right, for the protein A, right. Similarly, you can convert it for the protein B, answer will be 10 raised to minus 10 raised to plus 9. So you can see what is the vast difference is there between association and dissociation constant, right. Association constant is 10 raised to 6, dissociation constant 10 raised to minus 6, right. So a protein that has been having a ligand that has been binding with 10 raised to 6 affinity, right, to the protein, right, it dissociates from the protein with only the value of 10 raised to minus 6. It's a beauty, it's a beauty. So let us see now another problem, right. So an antibody binds to an antigen with a Kd of 5 to 10 raised to minus 8 molar. At what concentration of antigen will be the theta value be 0.2 molar? So here the antigen act as a ligand and whose concentration we have to find out, right, and you are given with the theta value and the Kd value. So you have a very simple equation, concentration of ligand is equals to theta into dissociation constant divided by 1 by theta. So if you place all this value of theta, that is 0.2, that is given to you, Kd 5 to 10 raised to minus 8, I am sorry, it is 10 raised to 6 minus 8, and 1 minus theta, that is 0.8, right. So you will have the concentration of the ligand as 1 to 10 raised to minus 8 molar. So you are getting the concentration of the ligand from this, right, from the simple equation. That is also been given in the Larringer book with the same reference, right. So thank you friends, and your suggestions always welcomed at a given email ID gopes938@gmail.com. Your next video will be on enzymes, and please watch and share this and upcoming videos, right. See you soon. Thank you.